Thank you.
I got it, Susan.
Thanks, John.
I guess I'm compatible.
Oh, Susan Sadikova's going to
Good.
give it up. Oh, okay, Susan, you're good now. Okay, folks. Let's start. Woo.
It's only 10:02.
I've got 7 o'clock. What time do you people have? Okay.
Yeah, you can still talk.
No, it is 7 o'clock.
Oh, it's 7. Okay. This clock is the only reason off. Okay. Welcome, everybody, to the March meeting of the Kingston Centre RASC. And welcome to those who are on Zoom. We were going to try YouTube tonight, but we're having a little bit of technical difficulties. So we'll catch it on the replay. First, I want to state our land acknowledgement that Queen's University is situated on the territory of the Haudenosaunee and the Anishinaabe Nations, and we respect the land that we meet on. A few announcements. Wednesday, social Zoom time for me. Chat list or contact the executive and we'll get you set up. Excuse me. May 5th to the 7th is the 2003 RASC General Assembly, and tickets are on sale, which are online on the website. The Top 10 Binocular Tour by Alan Dyer is on the Sky News website under the Observing tab, as he's posted in a couple of social media sites, if you want to take a look at that. We ended up getting our Sky News copy today. So it is in the mail, and of course, the last one. So that's a keeper. Our next Queen's Observatory open house is March 18th at 7 p.m. Looking for volunteers for the deck, weather permitting and dependent, and there is a telescope on site, so you don't have to bring your equipment. Our next meeting is on April the 8th. Sorry, no, that would be April 12th. Again, our guest speaker will be Dr. Christine Larson, Secretary of the AAVSO, and she'll be speaking on women in astronomy, past, present, and future via Zoom. Also, not sure if we can show this. Yeah, we have solar viewers here for the upcoming eclipse. In 2024, the center executive agreed to purchase some, and we have, and we're going to want to hand some out at Science Rendezvous this year, and we're going to have a poster set up, mainly because this is our only big event that the center will be at before the eclipse in order to reach the public. But we're sort of hoping to get more eclipse viewers through the RASC, but we went ahead and decided to order our own. So we're going to put them in an envelope, and under discussion how we're going to attach some safety information and stickers for the center information as well. So this is going to be, they'll be handed out soon. I just wanted to bring them in and show you. Also, center members have been asked by a student who attended last month's meeting, who was in cultural geography, if they would like to do a survey, and it would be anonymous. And the executive so far has agreed to this. So we're just waiting for her to send us the survey information, and we'll be sending that out to members. You want to do it, go ahead. If not, that's fine too. Our science fair is on March 30th and 31st. I don't know if Bruce is online. But he has a couple of people that are helping out for judging. And thank you to both Andrew and to, oh my goodness, Graham Hay for helping out again this year. And Science Rendezvous again is on May 13th. And we are looking for volunteers for Science Rendezvous. So if you would like to help, okay, Rick, I will need the size. Oh, and Lori. Need the size for your t-shirt, and if there's any dietary restrictions, just let me know by email, okay? And deadline for that is in April, so I need to know fairly soon. And that being said, those are the small announcements that we have. And David Levy, are you online?
Yes. Yes, I am.
Okay, David, you are up to introduce our poem for this evening.
Well, thank you. It's a Tucson tradition every March to do something called the Tucson Festival of Books. And so I decided to choose for our poem today a poem about books. It wasn't easy to find. I only found two, actually. One, of course, was John Keats' famous poem on first looking into Chapman's Homer. But the one I'm going to use is Robert Louis Stevenson's storybooks. There in the night where none can spy, all in my hunter's camp I lie, and play at books that I have read, till it is time to go to bed. These are the hills, these are the woods, these are my starry solitudes, and there the river by whose brink the roaring lions come to drink. I see the others far away, as if in firelit camp they lay, and I, like to an Indian scout, around their party prowled about. So when my nurse comes in for me, home I return across the sea, and go to bed with backward looks at my dear land of storybooks. Thank you very much for letting me quote this, and back to you.
Thank you, David. It was wonderful.
Can you make a note that you're having audio difficulties? Sorry, folks, people on Zoom are not talking to speakers again this time.
We are having issues with audio in the room. So if you do have questions for those who are in Zoom land, we will have to repeat them so that everybody can hear them. Okay, our guest speaker this evening is Professor Laura Fissel. She is an astrophysicist in the Department of Physics, Engineering, Physics, and Astronomy at Queen's University. Her research focuses on building stratospheric balloon-borne telescopes, which operate above most of the Earth's atmosphere, so almost in space. She uses both balloon telescopes and telescopes on the ground to study the birth of new stars and planets. Professor Fissel received her PhD in astronomy and astrophysics from the University of Toronto in 2013 and joined Queen's University in September of 2019.
Okay, I think the microphone's on. Can people on Zoom hear me? Oh, I'm getting a thumbs up. That's great. Okay, so
We have to unmute.
no, I think I am
you
unmuted.
don't. No,
You're
no,
good.
you're good. You're good.
Okay, cool. All right, hi everybody. Thank you so much for inviting me to come and talk to you today. So I'm going to be talking about kind of a different form of astronomy than maybe you're familiar with. So I'm sure you're all familiar with like gorgeous images from like the Hubble Space Telescope and from the James Webb Space Telescope now. And of course you're all very familiar with telescopes on the ground. Okay. So what I'm going to talk about is sort of an in-between form of astronomy, which is not from the ground nor from space, but kind of from the boundary between the two. So actually doing astronomy on a telescope with a telescope that is dangling from a stratospheric balloon. Okay. So just an introduction to me. I'm an assistant professor at Queen's, and I'm an astrophysicist. And so I joined in the fall of 2019, so right before the pandemic kicked off. And yeah, I use telescopes that other people have built, right? So for instance, I've used telescopes in Hawaii, in Australia, in Chile. So this is a picture of the Australia Telescope Compact Array in Narrabri, New South Wales, where I did some observations a few years ago. And I've been to Mauna Kea and done observations there as well too. But I'm also a balloon astronomer. So I build telescopes that fly on these giant helium balloons. Okay, so this is my balloon telescope. Okay, that's actually my PhD thesis project. And I am therefore a balloon astronomer. Okay. So what's a stratospheric balloon? Well, it's a helium balloon. So sort of like a super large party balloon. They are made out of polyethylene. So imagine like the material that like a sandwich bag is made out of, but half as thick. Okay, so that's what these helium balloons are made out of. And they're filled with helium gas. And when they're fully inflated, the largest ones, which can lift a couple tons, are huge. They're about the size of like a football stadium. Okay. And they can lift payloads up to about 46 kilometers. So they can get really high, right? So more than 3 times as high as like a jet plane would fly. And so that's really, really great for doing a lot of kinds of observing. And I'll hopefully justify that a little bit more. So here's sort of a little cartoon. So here's a picture. Actually, this is the same balloon telescope that I showed you before. So that's the telescope, this little tiny speck down here. The rest, this is the balloon. And then you can see a little bit of parachute up there as well, too. I'll show you kind of a clearer view later on. And so this is just a little cartoon that shows where things fly. So you can sort of see the different layers of the atmosphere. So the stratosphere is above the tropopause. It's above most of the ozone layer. And it's basically where you have the atmosphere no longer being heated by the ground. Okay. So it's the stratosphere is more heated by like the ozone layer. And so planes fly at much lower altitudes. So that's very, very nice. So we don't have to worry about interacting with jet planes or anything like that. And again, we can get very, very high. All right, so why would you build a balloon telescope, right? Well, the answer is kind of in this picture, right? So this is a picture that was taken from a balloon telescope, the Spider balloon telescope, just after it launched from Antarctica. Okay. And so this is a view, if you just sort of look out from one of these balloon gondola platforms, of what you would see. Okay. And you can see that you are above almost all of the atmosphere, right? So you can see the atmosphere, this sort of, there's this kind of band of atmosphere kind of along the horizon, along the Earth's limb. But it's, it's not quite as good as being in space, but it's almost as good as being in space. Okay, so we are above about 99.5% of the Earth's atmosphere at this altitude. And so why do we want to, what are we actually trying to do with these telescopes? So we're trying to understand, the physics of how the universe works. But we're also, I think, kind of doing some space exploration as well, too, right? So if you think about the most distant spacecraft from the Earth, man-made spacecraft from the Earth, those are probably the Voyager probes, okay? And both of them have been going very fast for a very long time, but they're still less than 1 light day away from the Earth, okay? Whereas the nearest star, Alpha Centauri, system is 4.4 light years away. Okay, so the prospect of actually sending something to another star is a very, very long time away. Okay, but we can still explore the cosmos by building really powerful telescopes. Okay, and so here's an example. I'm sure you've all looked at many objects in this region. So this is the Orion. You can see a lot of really famous observing objects. So there's the Flame Nebula, the Horsehead Nebula. And if you zoom in, this is a region that's forming a lot of stars, but we only see the dust, right? But if we can switch to the infrared, which is what's shown in this last image, so we're no longer looking at optical light, we're looking at infrared light, then you can actually start to see some of the material that's forming the stars start to glow, right? So if we want to be able to study how stars form, we need to observe that material, and therefore we need to look at colors of light where we can actually observe what's going on in these star forming regions, rather than just having starlight, optical starlight, be extincted by by all of the dust in these regions. Okay, so if we want to observe these regions, they're very, very cold clouds of gas and dust in our galaxy. That's where stars form, right? So if you look up at the Milky Way and you see all the dark patches on the Milky Way, that's where all of the dust and gas is, and those are the regions where the next generation of stars might form. So it's not dark, obviously, because there are no stars in that region of the Milky Way. It's dark because there's a lot of dust, and the dust is blocking the starlight, absorbing the starlight, okay? So if we want to observe these clouds, they're very, very cold, then we want to look at other colors of light. So the color of light that the objects emit depends on their temperature, right? So the sun or other stars are very, very hot, and therefore they emit invisible light. People are much colder than the sun, right? So we tend to emit in the infrared, right? So this is a picture of a guy wearing glasses. I think he has a garbage bag over his hand. And so you can see the light that he's emitting in the infrared here. And then these clouds of gas and dust, which are extremely cold, where new stars are forming. So they're just like minus 265 degrees Celsius, just maybe like 10 or 15 degrees above absolute zero. So the coldest you can get. They're even colder. So they emit further in the infrared, so in the far infrared. And so if you look at them in the optical, so this is, I think, Bernard, oh, what is it? I've forgotten, 59? Does anyone know? It's a very famous nebula. But anyway, it's just a little cloud of gas and dust. And, oh, does someone? Oh, okay. I wasn't sure if someone on Zoom was. Okay, are we good? Okay, okay. I wasn't sure if they knew the name of this little cloud. So anyway, it's just a little cloud of gas and dust, okay? And you can see all the stars in the background, but where you have the cloud, it looks dark, right? And that is because all of the dust in this cloud is absorbing the background starlight when it's on its way to us, so we can't see the stars through this cloud, okay? However, if we switch and we look at far infrared light, is this going to go? Okay, so there's the image over top. So this is a far infrared image. You can actually see this little cloud glow, right? And so we can see a lot more detail. We can see that there's something going on. There's something forming in this kind of high intensity region here. And we can actually map out the star formation in these clouds. Okay, so that's basically what we're trying to do here. Okay, so this is the cloud that I study most. So it's the Vela C cloud. You can only see it from the southern hemisphere. And this is what it looks like in visible light. So you can probably see some features. You can see that there's like an H2 region. So there's like some H alpha emission. There's some reflection nebulae as well too. These are kind of signatures of star formation. Okay, but most of the cloud, the gas that's going to form the next generation of stars, just looks completely dark, right? Because it's not glowing, and the dust is just absorbing any starlight that there is. Okay. However, if we go to the far infrared, so this is now an image with the Herschel Space Telescope. Okay. You can see all of this beautiful, beautiful structure, right? So where we had this H2 region, where we saw the H alpha emission, if you look in far infrared, right? So here, blue is kind of blue far infrared light. It's like 70 microns, and red is red far infrared light. So it's like 214 microns. And so the blue is where this dust, which is emitting, so what we're seeing is glowing dust grains. Okay, so the same dust grains that were absorbing the starlight. In the far infrared, we're seeing them glow, okay? And you can see that here towards this region is where we had this, the stars that have already formed, they're heating up the dust. That's why the dust looks blue in the far infrared, okay? And then you can see all of these different structures which are forming. You can see these beautiful filamentary structures, so where you have denser regions of gas which form stars. You can see little spots. That's where you have protostars, so regions of this cloud which are collapsing under gravity and forming the next generation of stars. And all of this really, really interesting structure that can tell us about the physics of how stars form. So this is what astronomers do, right? So we use, we can't actually go to any of these regions, but we can use telescopes that are sensitive to different kinds of electromagnetic radiation. And this allows us to look at different parts of the universe, right? So you can look at the X-ray, where you're looking at very, very high energy light associated with very high energy gas. In the optical, right, where you can see a lot of stars. And then in the far infrared or the mid infrared, where you see dust, and you can see the material that's going to form the next generation of stars. Okay. All right. So far so good, but it hasn't really explained why we need a balloon telescope, right? The problem is that most of colors of light won't make it through the Earth's atmosphere, right? So the Earth's atmosphere is basically mostly transparent to visible light, okay, and radio waves. And everything else, it's really hard to observe through the Earth's atmosphere. Sometimes for some of these, like some parts of the infrared, or going into high frequency radio waves, you can go to like a very high mountain. But most of the electromagnetic spectrum just doesn't make it through the Earth's atmosphere. So, in some ways that's good. It's probably good that we don't get a lot of gamma rays from the universe. That wouldn't be very good for our health. Okay. But if you're an astronomer, it's kind of frustrating because we really like to see these gamma rays, and it's very expensive to put telescopes into space. Okay. And even where we have the atmosphere is transparent, so again, something that you're all, I'm sure, very familiar with, the atmosphere you still pay a price for observing through the atmosphere. So this is kind of a short exposure time image of two stars, and you can basically see kind of like a speckle pattern, right? So basically the image, because of the seeing, right, because of all the atmospheric turbulence, the image of the star becomes distorted. And so if you integrate for a long enough, if you take a long exposure time, then you're going to get a blurred image of the star. Okay, so even if you observe from the ground, you can still get blurring and other effects from the Earth's atmosphere. So the light that I'm interested in observing to study these star forming regions is in this region, where you can see that the atmospheric opacity is basically 100%. So that means no light gets through. Okay, and so this is where I really want to map in order to study star formation, right? However, we just can't see through the atmosphere. Okay, so we can try to get above the atmosphere. So you can do this a little bit, as I said, by putting your telescope on a big mountain, but it's still really hard, right? The atmosphere is still way bright, much brighter than the emission from whatever object you're trying to see. Okay, so you can try this, but you won't be very sensitive. Okay, of course, the ideal thing would be something like Hubble, which is shown in this image, or the James Webb Space Telescope. Put your telescope in space, right? However, there isn't enough funding to build a lot of these space telescopes because they are so expensive, right? Like the James Webb Space Telescope was over $10 billion. Usually for a good sized space telescope, you're looking at like at least $1 billion. And, governments and funding agencies just don't have that kind of money to build many of these. It's a lot of work to get them approved. So what we can do is use balloons. So balloons aren't quite as good as space, but they're much cheaper, right? So for a telescope that would cost, $1 billion in space, we can build it for like a couple of $1 million on the ground. Okay, and so this allows us to do science for cheap that would otherwise require a space telescope. It's also much faster, right? So if you think about how long it took to build the James Webb Space Telescope, it took decades, right? Because it's very expensive to put this telescope in space, and so they have to be extra careful that everything works and they only get one shot, right? Whereas a balloon telescope, you can typically build it in a couple of years, fly it, decide that you want to change some things, rebuild it, fly it again in a couple of years, right? So it's much more flexible, and it's also really good for students. So for instance, like I worked on a balloon telescope as a graduate student. There's no way they would have let me work on like a space telescope like JWST, right? Because what if I did some soldering wrong and that broke the space telescope and they lost $10 billion? Like that's just not going to happen, right? So, but a balloon telescope is really great because it's relatively cheap and you can get a second chance to launch it. Okay, so hopefully I've convinced you that you could do a lot of that stratospheric balloon is a really great platform for astronomy. So here's just a plot to kind of make it a little bit more concrete. Oh, it didn't show the axes. Is it going to show the axes? No, it's not. Okay, that's fine. I can tell you what they are. So basically, what this is showing is actually how transmissive the atmosphere is. So 1 means all the light gets through. These are from atmospheric models. 0 means none of the light gets through. And so you can see a really great site like the ALMA telescope, which is in the Atacama Desert in Chile, even at ALMA, there's a lot of the kind of a range where we're interested in observing where the light just can't get through, right? It's opaque, okay? And then if you go to a stratospheric plane, like I don't know if you guys have heard of the Sophia Airborne Observatory, it's so much better, right? However, it's still not 100% transparent, okay? Whereas if you go to a balloon platform, it's almost 100% transparent along the most of this frequency range. Okay. All right. So balloons been around for ages, right? So balloons were actually the first way that humans were able to fly, right? So the first kind of recorded, verified balloon flight, untethered, was in 1783. In Paris. So they launched this beautiful paper and silk kind of telescope, which has lots of pictures of King Louis XVI on it as a decoration. And it was very, very ornate. You can see the two aeronauts in this image who were waving at the crowds. It was a hot air balloon, so they were had fuel that they were heating up the gas to keep the aerostat aloft. And I think in actual practice, they spent most of their time actually desperately shoveling on fuel because they were only flying just above the buildings, and there was a risk that they were going to crash into the buildings of Paris. But that was the first kind of untethered balloon flight. And then a couple of weeks later, or I guess not very many weeks later, physicist Jacques Charles actually had the first gas balloon. So it was hydrogen gas, and he brought scientific instruments. So it was actually the first scientific balloon flight. He was a physicist who launched the balloon. He had his assistant in the basket as well too. They had a valve so that they could safely descend, very important, and ballast. And then once the balloon landed, he made his assistant get out. With the kind of lower weight, the balloon kind of shot up again. And he ascended to 10,000 feet, nearly froze to death, and became the first person, as he says, to see the sunset twice on the same day. And then he descended again, and he never flew again. Okay. And so there's a really fascinating history of ballooning. It's really, really interesting to read about all of these kind of daredevils. But in like the 1800s, scientific balloon flights became more common. So it really gave scientists access to kind of the third dimension. So suddenly they could study the upper layers of the atmosphere. So this is a picture by Albert de Sondier. He and his brother did a lot of balloon flights and studied the atmosphere. However, there was a risk because, if your balloon was descending too quickly, right, and you didn't have enough ballast, oftentimes you would have to throw your scientific instruments overboard as well to kind of save your life, right? So it was very hazardous. Okay, so there's been some great science done more recently from balloon-borne experiments. The most famous is Victor Hess, who showed in 1912 that actually he had a machine that could measure cosmic rays, so these, which at the time they thought was maybe a form of radiation. And he showed that cosmic rays are actually not coming from the radiation from the Earth, but have to be extraterrestrial, because he had basically something that could measure these charged particles as they came in. And he found that as you actually go higher, the incidence of these cosmic rays actually goes up rather than goes down. Okay, and so he later won the Nobel Prize for this. It took a while for telescopes to balloon astronomy to become a thing, because you have to go very, very high to get the excellent conditions, and you can't just you have to point a telescope, right? So before you had automatic controls, that meant you had to send someone up. Right. So the first kind of telescope to go in a balloon was a father and son team, Charles and Antoine Dolphus, who were the first to take a telescope to the stratosphere. They had kind of like a sealed capsule to try to keep themselves alive, because again, there's very little air. So that was the first instance of actually taking a telescope. So of course, modern stratospheric balloons, as I said, are huge, right? They can lift very heavy payloads, and the biggest ones are like the size of a football stadium when they're fully inflated, right? And so they're very, very different. And then the other thing that's important is that now we don't have to send people up with these telescopes, right? We can just build in motors, have computers that control the motors. We can have cameras which take pictures of the sky and figure out how the telescope is oriented. And we can have computers basically run the entire experiment. So it's much safer because we don't have to like send students or professors up to the stratosphere, which would not go over very well with the Queen's safety officers. So we can do a lot of science. There are a lot of different launch locations that are used. So actually the nearest one to us is in Timmins, Ontario. The Canadian Space Agency does launches from there. There are some in the States, so Fort Sumner, New Mexico, which is very close actually to Roswell. A lot of balloons go that way. And also from Palestine, Texas, which is where the NASA balloon headquarters, well, the kind of balloon facility is. And then Kourou to Sweden, so launching from northern Sweden, landing in northern Canada. And then the longest flights right now are from McMurdo Station, Antarctica, where you launch from McMurdo Station, which is on the coast, basically just south of New Zealand. And in the summertime, the winds form like a stratospheric vortex and just go around and around the South Pole. And you can get up to, I think the record is like 2 months for a flight. Okay. All right. So here again is that picture from the Spider telescope. So let me tell you about the telescope that I've mostly been involved with, which is the balloon-borne large aperture submillimeter telescope, or BLAST for short. Okay. So BLAST is really designed to look at this far infrared light. It's mapping the glowing dust grains, which are mixed in with the gas, which will form the next generation of stars. Okay, and so by studying the glowing dust, we can actually map out the star formation. And because we observe in multiple colors, we can also measure the temperature of the dust as well too. So we can figure out the mass of the dust, we can figure out the temperature, we can figure out whether clouds of gas should be collapsing under gravity. So we can do a lot of really interesting science. So it was an international collaboration. So the first telescope, which was actually before my time, had a couple of different flights. So it had a 1.8 meter aluminum primary mirror, so pretty big telescope. It had, instead of like a CCD camera, it had bolometers. So basically they measure, the light is incident on the bolometers, the far infrared light increases their temperature and therefore changes the resistivity of the bolometer, and then we can basically read out the temperature increase. It had, to keep the electronics in the detector sensitive, we had to cool everything down to 0.3 degrees above absolute zero, so very, very cold. And then we had a whole bunch of different sensors and motors to basically control how the telescope points and to make it be able to point anywhere on the sky, and a lot of computer code to get everything to run, because you can't necessarily communicate with the balloon telescope once it's afloat. So they had a couple of different science flights. So one from Sweden, landing on Victoria Island, and one from Antarctica, where they did like one orbit around the Antarctica and eventually landed on the plateau. More on that in a bit. Okay, so I wanted to show this movie. I'm not sure if the sound is going to work for the people online, so I'm going to start it. But hopefully people online can let me know if the sound isn't working. The sound hasn't started yet, so. Okay, I'm not hearing anything. You should definitely be hearing something now. Are people online hearing?
Not hearing anything.
Okay, let's try this again. Can I like just put the microphone next to my speaker? No, I didn't hear anything, and there should be sound.
Is that your volume all the way up?
Yeah, it's all the way up, but I don't have the the sound on. So maybe could I like unmute? Am I muted? I'm muted.
Go ahead and try that and then try again.
Okay, I think we're gonna get echoes. Can we maybe mute there?
Okay.
Okay, let's try this again. Let me just go in the middle.
Let me see. Several
Here we
storms
go.
come through. We didn't have hail or fog.
Are people on the Zoom hearing us? No? Okay, we're gonna try this again.
Really
Oh, you were
hitting
hearing it. Hearing it. Okay, here we go. Try this again.
There it goes. Here's
Start from the beginning.
I think it looks really good. We didn't get rained on. We didn't have, let me see,
Hail,
several storms come through.
No, that
Anything that really went
it only works when we're both on.
There it goes. Here's the release.
He's doing good. He's doing good.
You have this instrumentation you've taken care for, and designed for years, and now all of a sudden it's just hanging from a string and it's out of control.
Okay, Joe, you can just start easing out just a little bit, just to make sure we can move, okay? You doing good?
Yeah, this whole thing is going to get flown on a balloon. It's going to fly from Sweden to northern Canada.
What we're trying to do is really revolutionary. With this telescope, we want to find out how stars were formed, how galaxies were formed.
Now hold it right there. Just keep going with a little speed. A little more speed, Joe.
This recovery is going to be far more difficult than I had anticipated. We have a polar bear spotter.
Oh yeah, definitely. Get a polar bear, 1-2 shots, it'll take it down.
A little more right. Walk it, walk it.
I've been out of town this year for about 165 days. Hey, Thomas, you there?
Okay, get ready to stop. Okay, Wood. Okay.
As a Christian, when I study the universe, I'm learning more about the God who I already believe in.
I have not really any reason necessarily to believe. If you want to take it from a purely scientific point of view, I have no evidence either way.
Back up, back up, back up.
Wrong way. Door. We gotta fly.
Astrophysicists have the opportunity to revolutionize what our culture thinks of our place in the universe. It's going to be more mind-blowing than when we figured out that the Earth was not the center of the universe. It's going to change everything.
Back up.
Oh, they're stuck.
Let it go.
Release it.
Go forward, go forward. Stop.
Oh, you're fucking kidding me.
Stop. Go forward, go forward, go forward, go forward, go forward. Keep coming, keep coming.
Okay. So turn this back on. Hopefully you can still hear me. I'm gonna turn. So I'll mute my end again. Okay, hopefully that's good. I'm going to turn down the volume on my computer too, so you can hear that. So this is that was a movie made. Oh.
We found his fingerprints on 2 of the dead bodies, including Ensign Blevins. He's not in any American database, but he is.
I don't know what that was. Okay, so hopefully you can still hear me. So that was a movie made by the brother of actually the scientist who's in charge of BLAST. And so he made a documentary about their flights. So the last part where the telescope, when they were trying to launch it, was sort of colliding with the launch vehicle. It was actually because one of the people who was in charge of holding onto the telescope, their glove had gotten caught in the rope. So they did manage to release it, and they were able to get the telescope, and they had a really nice flight, and then they brought it down. Okay, and that's where the drama really started. So I'll see if I can. Oops, no, I didn't want to start that again. Okay, so here's a picture of BLAST descending on its way down. Okay, you can see the parachute and then the telescope. And then it landed. It was up on the Antarctic plateau. And then they were not able, unfortunately, to disconnect the parachute from the telescope, some kind of communications failure. So the telescope remained attached to the parachute, and Antarctica is a very windy place. So the next time they sent a plane over to see what was going on, this is what they found. Okay. So parachute acting as a giant sail, that's the telescope right there. Okay. And you can see this lovely drag path, which I guess is pretty easy to follow. So the telescope was dragged 200 kilometers across the Antarctic plateau and eventually got stuck in a crevasse field. Okay, so this is the end of the drag path, and you can see the BLAST telescope down there. It is still there because no one is going to go into a crevasse field to take out a 2,000-pound aluminum structure. However, this was actually a very successful flight because it turns out that when a telescope is being dragged by a parachute for 200 kilometers across Antarctica, a lot of things fall off, right? Including the pressure vessel, which contained all of the hard drives with all of their science data. So even though they lost a lot of the telescope, they were able to get the science data and make some really amazing maps. So I'm going to show you one here. So this is the BLAST map of, I showed you Vela C before. This is the entire Vela molecular ridge. So it's basically like 10 degrees of the galactic plane. But instead of observing in optical starlight, here we're observing in far infrared colors, right? So again, blue means hot dust, red means cold dust, and you can see all of these really, really interesting structures. So you see like really skinny, long filaments of dust. You see regions that look like bubbles, where it looks like stars that have already formed have been heating and pushing away the gas and dust. So there's just tons of information about star formation. And so what they did is they counted up. Oh yeah, you can also zoom in and see it in far more detail if you zoom into one of these regions. And then these kind of like bright spots, that's where a star formation is occurring right now. Okay, so these are regions that have started to collapse and form stars. And you can also take a look and basically see, count up all the regions that should be able to form and collapse and form stars. They have enough mass and they are cold enough that you would expect them to collapse and form stars. And so what they found is that if you calculate, okay, well, how many stars should be formed from this region and the rate at which they must be formed, it's way too fast, right? So if all of these regions that we think should form stars actually did, then there would be way too much star formation, which would be really not typical of the rate that we actually see stars forming in our galaxy. So what this means is that star formation must be much slower than we expect. So something slows it down, or most of the dense clouds of gas that we think should collapse and form stars won't. Okay, and so this is a big mystery, is what could actually be causing star formation to just basically our galaxy and our universe to be so bad at forming stars, so inefficient at forming stars. Okay, so why is our universe so bad at forming stars? Okay, and it turns out it's because star formation is a really complex process, right? So this is actually a computer simulation of what's going on in a star forming region. So you can see all of these really complicated structures. You can see these kind of jets of material that are coming out. So that's stars are very messy eaters. So some of the material that they kind of accrete through gravity, they actually just push back out into the cloud. You can get stars exploding. The gas is really turbulent, it's churning. And this entire region is also threaded by magnetic fields as well, too. So there are lots of things that make star formation inefficient because it's basically a really messy, complex process. Okay. So magnetic fields are something that we can actually study with this far infrared light. Okay, and so magnetic fields can slow down star formation because they affect how gas moves, right? So an example would be like aurora. You see aurora when gas is kind of moving along magnetic field lines. And so if gas is kind of coupled to the magnetic field, then it basically sets the preferred direction for the gas to move. So basically, if you had a cloud of gas that you wanted to collapse into a star, the magnetic field would try to prevent the gas from moving in the direction kind of across the magnetic field lines. Okay, so it can slow down through this way the collapse of stars. Okay, So could magnetic fields be slowing down star formation? We can actually map this by observing these dust grains, right? So these little tiny dust grains that we've been observing in the far infrared, it turns out they actually work like tiny little compass needles. They'll tend to align perpendicular to the magnetic field, right? So obviously, like a dust grain is way too small for us to observe, right? Like many, many light years away. But it turns out that because they're aligned, their light that they emit tends to be polarized, okay? So it basically has, the light waves have a certain orientation. And if we can measure this orientation, then we can actually map out the magnetic fields in these like distant star forming regions that are hundreds or thousands of light years away. Pretty cool. So this is what we did with the blast pole collaboration. We basically took the bits of blast which fell off before it got dragged onto the Ross field, including like our cryogenic refrigeration system. So we kind of like hammered out the dents in our cryostat. The telescope, the primary mirror, we actually had to replace because it was quite scratched. And we rebuilt everything else and put in a polarimeter so that we could actually measure the polarization direction as well too. And so this was my PhD thesis project. This is me in Antarctica. Basically everyone in red here was actually a student. So this is somebody who did their PhD, or at least part of their PhD dissertation on this telescope. Okay, so here's a picture of blast pole as it's being launched. Okay, so it's just been released and they're kind of gunning the engine on the launch vehicle, which is incidentally called the Boss. That's the name that they gave it. Releasing, getting out of the way so that the telescope can ascend. Okay, it flew at an altitude of 38 kilometers. This is the flight path around Antarctica that it took. So you can see it kind of ascends, and then you have the kind of this curlicue pattern. That's basically just caused by the fact that as the sun's altitude changes, the gas inside the balloon kind of cools or heats, and so it changes in altitude a little bit, and that changes slightly the wind direction. And so here's a picture. You can see the balloon. This is just as it's rising, the parachute, and then blast pole down at the bottom. So when they want to actually bring this down, didn't actually. Okay, I thought I had a video of that, but I guess it didn't copy. They basically, again, just separate the balloon from the parachute. Okay, and so that's how they bring it down. And then it lands on the ice. Antarctica is a windy place, so it usually blows over and falls over. And then you can send a plane out to it to actually recover all the pieces and get the data so that you can get your science and then maybe fly it again later. Okay, so we talked about magnetic fields. So here is what the same cloud looks like, but with the magnetic field lines. Okay, so the color here is basically the structure of the cloud. Okay, and these kind of lines over top, those are showing the magnetic field. Okay, so we can see a lot of really interesting stuff. And one thing that's really interesting is a lot of these really dense regions in this cloud, the magnetic field is actually like they're kind of at right angles to the magnetic field. Okay, and what that actually suggests to us is that maybe the magnetic field was involved in compressing the gas, right, or at least keeping the gas from moving across the field lines. And so it's sort of shaping some of these dense regions where we know the new stars are forming. Okay. And so we'd like to do this, but with many, many, many more clouds, right? And so to do this, we built a new telescope, which was called the Next Generation BLAST, or BLAST TNG for short, which was basically like a super version of blast pole. So new detectors, a bigger mirror, it could take more data because it had a larger a refrigeration system, so it could stay cold for longer, just kind of everything upgraded. And we were going to try to observe thousands of clouds. So this is a picture of our launch team. So again, I'm somewhere, oh yeah, I'm in the kind of funky hat here. And then that's blast pole hanging from the Boss, the launch vehicle in the background. And in the back here, you can actually see Mount Erebus, which is the southernmost volcano in the world, active volcano. So here is what the telescope looked like actually inside our lab space, so inside our high bay. So it's a very high ceiling space. Here's our the lead scientist, Mark Devlin, for kind of scale. This is our refrigeration system. So someone thought it looked kind of like a jug of Kool-Aid. So they made a Kool-Aid man face. And then I guess we posted pictures of this on like Twitter, and Kool-Aid saw it and they were like, oh, well, we'll send you a kit so you can make it actually like this. So this is like officially Kool-Aid endorsed cryostat. And then this is a picture of our detector array. So I won't talk too much about that, but we had really, really cool detectors, which can have, basically it's a new technology that allows you to have a really, really dense detector array with many, many, many detectors, so we can make even more sensitive maps. Okay, so we went down to Antarctica in 2019. So here's our flight from Christchurch, New Zealand. That's where you fly from. You take a US Air Force C-17 plane. We went to McMurdo Station, Antarctica, so that's where we basically lived. And every day we took a 40-minute bus ride out to the long duration balloon facility, which is where the US balloon program is. You get to see some wildlife. So that's me with some emperor penguins safely in the background. And then we put together the telescope. It took a while. We spent a lot of time testing it. And then we finally got to launch it on January 5th, 2020. And so this is where things get a little bit dramatic. So I'm going to point something out. So here's the launch. They released the balloon. Okay. This is the flight train, parachute. There's the launch vehicle with blast on it. Okay. And so just show you this whole thing. So you can see the balloon is spinning. That's not that weird. You can see it's actually kind of clamped here. And that's there's actually a collar which is designed to keep the balloon from billowing out, because the gas is going to expand when it goes up to the stratosphere. So they only want to fill it like a few percent. Okay, so they have to release that collar in order for the otherwise the balloon would pop, right? And so they have to do that before the balloon really ascends. So now what they're doing is they're starting to position the launch vehicle. It needs to go right underneath. Okay, so that they can, because you don't want it to swing back. So they're getting into position here. And so they want it to swing a little bit away from the launch vehicle. There they go. They just released it. Okay, now this might be hard to see, but there is something which is falling very, very quickly. Okay, and it sort of stops, hits the telescope here. And then the telescope starts spinning in the other direction. That was the collar. So that was the thing that was designed to keep the balloon from billowing out while they were filling it. It's about a, I don't know, 10 kilogram ball of canvas, which free fell about, a couple 100 feet. And here's a zoom in to see what it did. There's a hole in the back of our sun shields. And you can see little bits of mylar, which are falling from the telescope. So it was pretty bad, and it was pretty scary, and it made a loud noise. And I didn't show you the audio for this one because there was a lot of swearing. So yeah. So we were like, oh gosh, like that's it. Like I'm sure that like damaged and broke our telescope. But it didn't initially, right? We were able actually to take some data. We were able to point the telescope. We were like, okay, well, let's just see what we can do, and maybe we'll get some data. So that's the telescope, that's the balloon when it's up higher and it's fully inflated. However, just when we were finishing up our calibrations to get started on taking our science data, something happened, something very dramatic. The entire telescope pitched forward by about 4 degrees. All of a sudden, and then our motors would no longer work and we couldn't point the telescope. So we can't take data, we can't point the telescope. So we just had to end the flight. So we only made it very, very just up onto the Antarctic plateau, and then we had to end the flight. So what happened is when we launched, it did some structural damage to the gondola. And in particular, it damaged this bar up here. And that bar is basically designed to keep the cables from which the balloon gondola is suspended, to basically push them apart, right? So that we have more space to move the telescope up and down. And so that bar snapped, and then the whole thing kind of pitched forward. Okay, and so that was it. We couldn't take any science data. We did manage to recover a lot of the components of the telescope. There was a lot of damage, so it's going to be quite a few years, and we'll need to get some more funding before we can rebuild it. So that's what we're going to try to do next. But in the meantime, actually something that we're working on here at Queen's is a different type of telescope. So we're trying to demonstrate, I was talking with some people earlier about this, that you can use a balloon-borne telescope actually as part of like a worldwide network of radio telescopes. And so this is how they make extremely high resolution images. So for instance, maybe you've seen these images of like the shadow of the black hole in M87 and also in our own galaxy as well too. So these are the highest resolution astronomy images that have been made so far. And basically you use like the Earth as a telescope. So you combine telescopes from all over the Earth and you basically get the resolution of an Earth-sized telescope. And you could get to even higher resolutions if you could go to a higher frequency light. Okay, so or shorter wavelength light. But then there aren't very many sites where you can actually observe that kind of light from the ground. So a balloon telescope might be a way to actually get even higher resolution if we can prove that this will work. Okay, so this is something that we're working on now, and that's kind of the next thing that we're working on while we're waiting to have another go at this star formation, this polarimeter that I was telling you about to study magnetic fields and star formation. Okay, so basically the idea is that you just have a ground-based telescope, you have a balloon telescope, and then you need to measure the delay in the light signal between your ground-based telescope and your balloon telescope, and that gives you really high resolution information about the object that you're observing. Okay. However, you need to be able to know the position of your telescope to like a tiny fraction of the wavelength of your light. So for the telescope that we're building, that means we need to be able to track the position of our balloon telescope to less than 1 millimeter. So it's going to be a bit of a challenge, but we think that with really good accelerometers and a GPS unit, we can and some clever software, we can do that. Okay, so this is the next telescope we're building here, and we're planning to launch it from Timmins, Ontario in the summer of 2025. Okay. So I'll wrap up here and just to say that, scientific ballooning has really played a large role in the study of our universe. It's been responsible for some really important discoveries. And this allows us to do almost space science for a fraction of the cost of a satellite telescope. But it's definitely more risky, right? And so I've shown you some examples of like some really great data where the telescope was destroyed, some very nice data where we were actually able to recover the telescope, and a flight which was like a total failure because we were hit by something falling from above. Who would have thought? So it's definitely more risky, but it's you can get some really great science. And it's definitely always an adventure as well, too. So I don't know if I would ever want to just do balloon astronomy. I like to use other telescopes, which will, hopefully not have things, parts of the balloon fall on it. But you can do some really great science. And I'm going to continue to build these balloon telescopes because it's lots of fun. And when it works, it's wonderful. Okay, so I'll leave it there and take any questions.
Does anybody have any questions for Laura?
Oh, it's so bright.
Hello.
Yeah.
Is there much damage to the structure to the telescope and that when it hits the ground?
Okay, so I'm going to repeat the question in case people on Zoom didn't hear that. So when the balloon descends on the parachute and it hits the ground, is there much damage? So there's usually some damage. It's not going that fast when it hits the ground. So it's maybe going like, I don't know, 15 kilometers per hour when it hits the ground, but it has a lot of inertia, right? So generally you design the telescope, oftentimes they'll fly like what are called like crush pads underneath, right? So that absorbs a lot of the shock when it lands. However, like I said, especially in a place like Antarctica, that's very windy, the telescope's likely to fall over as well too. So there'll usually be some damage. We can limit that by making sure that we use up all the cryogens, and also that we turn everything off, so we power everything off, so that's also can limit the damage. It depends, like I've mostly flown from Antarctica, but I've known some people who've flown from like other places, And I have some friends who launched a balloon from Timmins, and their telescope landed in a tree. Okay. I know that my PhD advisor, he flew a telescope which landed in a lake or a pond. I think it was pond. It was for like cattle. And there are stories which I don't know if I believe that people have shown up in the U.S. to recover a balloon payload, like a balloon experiment, and have found like bullet holes in their payload. Yeah, I don't know if that's true or not. That's just maybe just stories that the NASA guys tell, which aren't really true. But it depends on where you land. There'll probably be some damage, but it's usually not that hard to repair. And you usually design your system so that it can survive that. Yeah. Okay.
Oh, we're waiting for Zoom. I have a question. I'm a big fan of beam stocks, the low Earth orbit.
Mm-hmm.
How's the strength of material these days to actually tether the balloon so you don't have to worry about it turning them up or being destroyed on land?
Yeah, it would be really hard to make a 38-kilometer long tether, right? I think it would be, I mean, it's definitely harder to make a space ladder, right? But it would, if you think about like conventional materials, that would be really heavy. It would be far heavier than our 5,000 pound thing. You could maybe do like a tether that's like a couple of kilometers up, but at that point you might as well just go to like a mountain. Right. I also think for something like the interferometer project that we're doing, that would actually make it harder, right? Because one of the things we need to do is be able to correct for all of the vibrations, right? And so if you're tethered, but the wind is trying to blow the balloon, then you're going to have a lot of vibrations, and it's not going to be a very kind of stable environment for your telescope, right? Oh, sorry, I guess I should have repeated the question. I don't know if people on Zoom heard that. No, it was a great question. Yeah. But
Pictures of your balloon, they look an awful lot like Chinese.
Okay, so the question is, am I a Chinese running Chinese spy balloons? Okay. The answer is no. Okay. Yeah, it's been really interesting to see balloons, like stratospheric balloons, come into the news. So that's been like, oh, they're talking about balloons. I hope this doesn't like affect our ability to launch them, right? Yeah, it's interesting. I mean, I guess they've proved that they can shoot down balloons if they want to. That one was actually the one that they think was a Chinese spy satellite, was flying at a lower altitude than what our balloons fly at, but not that much lower, right? It's, yeah, they're it's kind of hard to stop someone from launching a balloon that could go over your country, right? You can't really direct normally where these balloons go, right? They just go wherever the atmospheric wind pattern.
We're not hearing anything on Zoom?
Yeah, I'm not hearing anything anymore.
Should I turn my microphone on and off?
Hear us now.
We weren't hearing anything up to that point.
Can you hear us now?
Now we can hear.
Okay.
Can you hear me?
Yes, I can.
Okay. All right. I've forgotten the question. Oh, Project Loon. Yeah. Their idea was that you could use balloons to provide like a Wi-Fi service, right? And they were actually flying at much lower altitudes where there's a lot of variation in the wind direction with altitude. And so they could actually use the kind of, they could control how much of the volume of their balloon right? And basically control the altitude at which they operated so that they could actually steer and try to stay in a particular area, which was kind of cool. But they shut down that program a few years ago. There are opportunities to do that, but usually not at as high of altitude as we fly. So we try to get to a place where the winds will likely take us where we want to go, and not where we don't want to go. Like, for instance, over many countries which would not be happy with you flying a 5,000-pound telescope over their territory. So.
May I ask a question from the chat?
Okay, sorry, I'm not sure which.
Susan?
Yep.
Do you get approval for launching balloons from aviation?
So the question is, do we get approval from aviation agencies to launch balloons? Yes. And in fact, for the size of balloons that we launch, there's no way that like a science team could launch it, right? It would be really, really dangerous. You need very specialized training to do that. So those kinds of big balloon launches are actually handled by the space agencies. So NASA has contractors who do their launches. The Canadian Space Agency works with the French Space Agency, CNES, to do their launches. And basically you have really trained teams of like riggers and engineers who are responsible for this. Some teams who have smaller payloads, they'll do like hand launches. Sometimes they'll do them themselves. So there you have to be very careful about making sure that you have the correct permissions where you launch, and also coordinating if your telescope is going to go into like a new airspace as well too, so that you don't get into any trouble. But lots of people launch balloons. Like you can buy a balloon which can lift like 100-gram payload, right? And everything you need for not very much money. You can just buy all this stuff off of Amazon, right? And so there are lots of amateur groups, student groups who will like design their own payload, like their own mini space experiment, and just launch balloons, right? And that's not so far very heavily regulated. I'm wondering if that's going to change now after the incidents in recent weeks. And you're supposed to like check with the local aviation authorities and let them know what you're planning on doing, because your balloon will pass through the altitude at which like planes fly. So questions from online?
There was a question in the chat. Alan Dyer wanted to know, and you may have covered this when I was doing something else. Have high altitude balloons ever been used for aurora research, or is their altitude just not high enough to make useful measurements?
That's a really good question. It's definitely not high enough that you would be in like the ionosphere or the layers of the atmosphere where the aurora actually occurs. That tends to be higher. But I think that I don't know of people who've done aurora research with balloons, but that doesn't mean it doesn't happen. It might just mean that I don't know those people who are launching those particular missions. I know that I'm pretty sure we've seen aurora in some of we have like optical cameras which take pictures of like stars in the sky to figure out where we're looking. And I'm pretty sure that we have seen aurora in some of those images, which is actually a little bit annoying for us because we actually wanted to see the stars instead. We also see clouds, interestingly, in some of those images. So there's like polar mesospheric clouds. So they're at even higher altitudes than the stratosphere. And those cause us a lot of problems, actually, because again, they block out the starlight that we use to try to figure out where the telescope is pointing. Yes. Well, I'm not sure if you have to file flight plans in Antarctica. I'm not sure how like the aviation authority works in Antarctica. I know that like US planes are only allowed to fly over parts of Antarctica. But yes, if it's like a North American flight, then you would have to let the aviation authorities know. Of course, there's only so far that you can actually predict where the balloon is going to go, right? It will go wherever the winds take it, which might not be where you expect. So you have to have some contingency, I guess.
Another question. I would have thought it would be difficult to keep the telescope continually pointed to the correct point in space when the balloon is still moving along. I mean, that must be some fairly sophisticated control system, I think.
Yeah, it's not that well. Okay, so it is difficult, right? So we have a bunch of different motor controller systems. So for instance, we have like a flywheel, like a reaction wheel, so that is attached to a motor. So it's basically just like a big disc that we can spin to control the velocity of our gondola, so the angular velocity, so how it's moving. We have the telescope mounted on an elevation axis, so we can tilt it up and down. And then we can also, we have a motor basically where the telescope is suspended, so that we can actually twist that and transfer momentum, like some of the spinning motion up into the balloon itself, right? So we can control pretty well. And then we have cameras, which we use to observe the sky to figure out where we are pointed. We know where we want to be pointing. And so we can use our motors to look at that particular location. And actually it's the balloon gondola is actually pretty stable. There are high wind speeds, but you're above like 99.5% of the atmosphere, right? So they don't carry a lot of momentum. So it's you can it's actually mostly what the telescope experiences, because it's going at the same speed as the balloon, right? Because it's suspended from the balloon. Is if there's any difference in the wind speed between the balloon, the altitude of the balloon, and the altitude of the telescope, that kind of wind shear. So that's what the telescope will experience. But it's usually it's not that bad at these kinds of altitudes. Mm-hmm.
Okay, are there any more questions? Any more from the Zoom land? Okay, if not, thank you very much, Laura. That was excellent. We look forward to see what happens in 2025.
Thank you.
And
Thanks for having me.
so we're going to take a 5-minute break, and thank you again. We have some calendars for sale here for $10. And we have a David Levy book for sale. So if anybody would like to purchase these, come and see us. And we'll see everybody in 5.
Okay, folks, so we've rearranged some of the hardware. And I think we've got our camera back, and I think we've got our sound back. And Mark, what are you doing driving down the highway? Oh my goodness.
Yeah.
Just turn the volume up here a bit so we can try to hear you. Ah, Mr. K, maybe we should phone the OPP. So Elena, can you give me a thumbs up if I'm actually sharing the presentation of the agenda and the sound is good, obviously, since you just put your thumb up and the camera is working without difficulty. Okay, I think I know what's going on a little bit more. And there's a chat. What's the chat? Thank you. All right.
Look up at it, which is cool. And then there's lots of like in the ocean. They would also like bring out the divers. They have like divers who go down and collect. They would bring out like some of the creatures. They have like an ocean water lab and put them down there for people to go and like look at and things like
And it actually has wow. To hang out there under the ice. And that's
Kevin, what's your the audio?
Let me mute your.
Okay. Hello.
Tim is looking for a microphone. And we're about to reconvene. Okay, our audio is live. I've got the agenda up.
How many people in the room, Kevin?
11 people in the room, 22 online. Okay, folks, we're just about to restart. You are more than welcome to stay, but again, you have a midterm tomorrow. We understand.
I have anything else on my screen?
Okay, thank you very much. Bye. Bye.
Give you back the microphone?
The microphone is right there. You have it in your hand.
No, that's mine.
No?
Yeah.
Okay, I have this one right here. You have that one right there.
It's working. You hear me? No.
Yep.
Yes, we hear you.
Okay, thanks. Okay, so welcome back, everybody. So we are going to start off with the update from National Council from John Hurley. You're up.
Hello. I'm not sure what's going on, but my main computer is giving me a lot of static through my headset. So I'm not going to play with that anymore.
Can everybody out there in the audience hear John? You're a little quiet because we don't have room audio, so yell.
All right, so we'll try to give you a brief update on what has been going on at National Office. And let's see here. Briefly, though, there was a talk at National Council in December and February. That's for volume for us.
Works on the mic.
Okay, we're done with technical support for the moment, I hope. But National Council met in December 4th and February 5th, of which the board gave council a report on the finances, and they were not looking good. And so after the February 5th report, which was pretty much the entire meeting, of which center reps and presidents were represented, so there was a lot more people than usual, but the meeting was only for a couple of hours, so there were a lot more questions than there was time for. And the gist of it was they sent out a brief survey with 5 questions to the center and wanted a response by the end of that week. So we only had a couple of days to look at the questions and discuss as councils. And many centers sent the responses back. Here is a brief example of the 5 questions they sent us. They were trying to cut down overhead, so they thought maybe sending money to centers less than once a month would be a good thing, but we think that idea has died as not really going to help anything. There was some talk about whether we should go back to the days where we had a unified membership fee. Many centers responded with this, and there's a lot of feedback on variations of this and how it can be happened. If anybody's interested in any of that, please contact us and I'll let you know some of the results from other centers. There was some discussion about what to do with the family membership fee. It was very complicated. So there was talk about simplifying it because it was based on how many names you included on the family. So that might be getting simplified in the future. There we had, like I say, we had couple of days to discuss whether the society should be involved in the remote telescope. At the moment, it was costing the society money. And the society in the last year was bleeding a lot of money. So many centers reluctantly agreed that we'd have to liquidate that asset, which was many centers did not agree with, and many of us expressed our concern about that. As far as Sky News, it has been some discussed about what to do. And it has been decided Sky News is going to go defunct. There's been a suggestion that the database of all the past issues of Sky News should be made available to the RASC members for downloading and archive purposes, which we have not heard any response about that suggestion yet. There's been no response about what happens to people who have paid a subscription, the Sky News. There's been no response about what's going to happen with our membership fees, which we were told would include Sky News. So we're awaiting more information. As many of you have read through the emails, that this issue that you're getting in the mail now should be the last one. If anybody's got any questions, we'll try to address them. If anybody's looking for any more details, please email me and I'll see what we can share. Certain numbers from the financial reports we can't share until they are been finalized for the year-end statement that will be in the annual report. But there's a lot of changes coming to national office. There's a lot of some of the staff have agreed to take a leave. Some have moved on to other things. There'll be a reduction, so hopefully things will be able to carry forward. Randy Atwood has taken over the position of the executive director, and until a more permanent one can be found to fill in for Phil Groff. That's about it at the moment. If there's any questions.
Are there any questions from the floor? Any questions from Zoom land?
I see nothing in the chat yet.
Okay, well, if you do have a question, please don't hesitate and contact John, and he will share what he can. Thank you, John.
Yeah, thank you.
Next up, Rick Wagner, what's up in the sky for March?
Hello, hello. Well, good evening, everybody. We hope March will have some more clear skies. I didn't look back at my records, but I've had like 14 observing sessions so far this year. I think last year I was up to about 30 by now. So
Sharing it, hang on.
oh, okay. Share me.
Sharing.
Oh, he's spoiling it. He's showing it all off. Everybody's seen it all. All right, March 2023. Local events, most of these are Queen's University Physics Department, the cosmology of dark energy radiation. I've read the abstract on this. It looks really complicated. None of the others have any descriptions of what's involved, but exploring the compositions of exoplanetary material with white dwarf stars. 14th of March is something we can all enjoy. Pi Day is 3.14. It's also the day you make apple, cherry, flapper, whatever kind of pie. It's an excuse to have a pie. That's all I know. 16th of March, high energy neutrino experiments. The Queen's Observatory open house on the 18th. Connecting the observable to the non-observable at a crossroads. I don't know what that means, but it sounds more like philosophy than physics. A special discussion on experiments in Canada. No specification on what kind of experiments. The fast radio sky, of course, we've heard about that with Chime and so forth. And at the end of the month, sparkling discoveries by JWST in galaxy clusters. So that one might have some pretty pictures. As far as I could tell, none of these will be on Zoom. They'll all be in person only. Nothing at the BAA online anymore that I can see. AAVSO webinars, they're having their regular how-to webinar on the first Saturday of April. No topic has been decided yet. Hours of darkness, you can see as we get towards later in the month, we're getting towards the equinox. The sun is on the equator, so it's at 45 degrees north and or 45 degrees altitude rather. And the night times are getting shorter. It's very depressing. So up in the sky, well, sort of in the sky, 12th of March, boo, daylight saving time starts at 2 a.m. And we all operate in universal time, so you have to subtract 4 hours instead of 5. Last quarter moon on the 14th. From the 16th through till maybe the 26th or so, you can look for the zodiacal light. It's a big cone of faint light extending up and to the left from the western horizon after sunset. And then the Gegenschein is a very, very, very faint glow, 8 to 10 degrees across, just down and to the left from the nebula, sort of about midnight. 20th of March, we have the vernal equinox. So spring, astronomical spring begins in the Northern Hemisphere. The 21st of March, asteroid or dwarf planet rather, number 1 Ceres at magnitude 6.9 is at opposition. And we'll have more about that later. 21st, full moon, the middle of the day. 22nd of March, this should be very pretty, a 31-year-old crescent moon. So this is going to be a very, very thin crescent moon, just 1.5 degrees from Jupiter shortly after sunset on the 22nd. On the 23rd, the following evening, Venus is much higher and up and to the left of Jupiter with a slightly thicker crescent moon in between the two. Starting on the 26th of March, this will be kind of interesting if you want to see Mercury because of course, Jupiter, as we go through the months, it's approaching the sun, so it's gradually getting lower in the twilight sky. Mercury, on the other hand, is coming around the backside of the sun and racing up to what I think is going to be its best, greatest elongation east. So it's going to come racing up as Jupiter is moving slowly down. You'll be able to watch it over a period of about 5 nights or so, zoom past Jupiter. On the 28th of March, first quarter moon, full moon on the 6th of April, and then again on the 11th of April, just before our next meeting, the greatest elongation east of Mercury. So that it'll be its highest point sort of above the horizon after sunset in the west. Small bodies. So Ceres happens to be going through its opposition, going through the Coma Virgo galaxy cluster. So it's going past a number of objects, 5 arc minutes from M91 in the early morning of the 10th of March, just a couple of days, 3.3 degrees. I've only picked out sort of the biggest and brightest galaxies here. 3.3 minutes from 4421 in the evening, 3 minutes from 4396 in the early morning of the 22nd. On the evening of the 2nd, it's 4.3 arc minutes from NGC 4379. Then on the 25th, it actually goes by M100, which of course is one of the biggest face-on sort of grand design spirals. So it's going closest during the day. So in the morning, you can catch it 6.3 arc minutes to the lower left of M100. And then that evening, it'll be 4.4 arc minutes to the upper right. And of course, all these distances are from the center of the galaxy. And some of these galaxies are a significant fraction of this size. So minor planet's going to go very close to these things, be very photogenic. We have one asteroid occultation, 1977 Shura, named after Alexander Kosmodemyansky, who was a hero of the Soviet Union, died in Second World War. How that gets you an asteroid, I don't know. But anyway, it's a 12.2 magnitude star, which is pretty faint for the normal things we look at. So imaging it, unless you got a fairly large telescope, you won't be able to get good time resolution. But visually, a 6-inch, 8-inch telescope will probably show it. The asteroid itself is 17th magnitude. It's very small. So 5.2 magnitude drop, and the maximum duration is 0.9 seconds. So it's just going to be a little blip if you see it. And you can see here, Kingston is within the path. Those west of Kingston are in the 1 Sigma area. For those of us up to the northeast and far east, we're outside the path, so we won't see it. And the star is between Auriga and Gemini. So at the time of the occultation, it'll be sort of about 45 degrees up, almost due west. So if you have a decent western horizon, you should be able to see it. Any questions?
What was the date
I have
on
to
the last
remind
one?
myself, the 2nd of April. Actually, that'll be on the 1st of April because it's at 2 hours. So it'll be.
And is it -4 or -4 or 5 hours?
It's 4.
Rick, we have 2 comments from the chat.
Yeah.
Susan also picked up, you said a 31-year-old moon.
31 hours.
Where is your mind? Yes. And the other one, Mark K asks, did you mention the new moon? We always want to know when the new
Did
moon
I
is.
not mention a new moon?
On that slide.
We didn't have one this.
So you're going to take the first full moon, Mark, and add 14 days.
No, there isn't one this month. It must be the 21st. Yeah. Yes. Well, yeah, because the 22nd is the thin crescent moon. So yes, so that should be a new moon. Yeah. Any valid questions?
No.
Wisecracks from the peanut gallery? All right, thank you very much.
Okay, thank you, Rick. Let's hope for clear skies. Okay, next up is our members observing reports. And I think we'll try to go from Zoom land first. Got to see a list of people.
Yep, to the sec.
Okay, start from the top. John Hurley, observing.
Did some solar today, but haven't processed it.
John has done some solar today, but hasn't processed it yet.
Okay, yeah, I know how that feels. I do have one picture to show tonight, though. Okay, Susan.
I think since the last meeting, I may have had 2 observing sessions, and that's been it. It's been a little bit grim. But one thing I do have is I bought a roof rake for the observatory. So now I can easily pull off all that extra snow, and I'm very happy about that.
Excellent.
Sorry, I missed that. What did she repair on her observatory? Did you spray it
New-
down with
A new snow rake.
a new
snow
snow
rake.
rake? Does that mean you sprayed it down with canola oil? What?
No,
Oh,
roof
a rake. A rake.
Yeah.
Ah,
Okay, Mark K.
Mark K said he had no report.
Okay, Bruce Elliott.
Yeah, so I've been trying to look at the conjunction, of course, like probably others. So I got a couple of pictures of it, but I didn't actually get to see it on March 1st.
We can't.
But I did so it turns out my daughter in Toronto, she was out with her son, and my grandson, and they actually got a picture of it, and I was kind of excited about that. So they sent it to me, and so apparently he, like my grandson, took it with a cell phone, and that's better than nothing, right? So yeah, so that was kind of exciting a little bit, and of course Kim kindly sent me the a 4-day series of it from somebody in the London, Ontario center, and yeah, it's online, and maybe some of you already seen it, but it's really quite beautifully done. Camera exactly in the same place each of the 4 days. So anyway, that's my excitement.
Okay, thanks, Bruce.
Sorry, folks, we couldn't hear Bruce too well, and that's,
You may have to listen to the replay.
yeah, listen to the,
Oh, sorry,
the
I-
audio will be
No, no,
perfect
not you, Bruce.
on
We
the
have
Zoom
some
recording.
audio issues here in the room.
Yeah.
Okay.
Okay, thank you. Next up, Fred Barrett.
Not much this month. I've been busy with a lot of other things. Of course, I had a good time watching Jupiter and Venus converging on each other, and I got a bunch of, they're just cell phone pictures. But it was fun. I talked a lot about it to local people and such, so lots of them went out and had a look at some of the nights. I was happy with that.
So Fred, were you able to see it on the 1st of March?
No, it was clouded over here,
Yeah.
but I got it February 28th and March 2nd.
Oh, good. Excellent.
So I was at, I'm involved with a play in Sherwood Lake, and I was out taking some cell phone snaps, and when people were arriving, I pointed it out to them, and these actors and such were excited. They never thought to look at the sky, so it was a nice way to remind them that there's stuff out there, and you should keep looking up.
Hey, thank you. Chris. Anything that you've been observing? Okay, carry on. Elena.
Well, I admire everybody that goes out there, but I'm not going to garden or do visual astronomy until it's above +12.
Yeah.
Okay. Okay, Getchen, anything to see? No. Keith.
No, I don't have anything. I think I mentioned it before that I was out trying to observe and I had too much weight on my white light scope and the whole thing went wacko. And I realized that with the micro focuser, which is a great big huge thing, was too heavy. So I ordered a new mount bar, which I received the next day, and I mounted it on. So I'm good to go. And of course, the other day we had this horrific wind and the scope was walking all around the observatory. So I couldn't do anything. I think that was yesterday. And today, when the sky cleared, unfortunately, I had an appointment. So when the skies are clear, I get screwed. And otherwise, I'm ready to go and it's cloudy. So go figure, right? That's astronomy. So that's it.
Okay, great. Thanks, Keith. Hopefully tomorrow it'll clear for you.
We'll soon find out. I'm looking out right now at the moon, which is just past full, and it's got a nice pile of cloud around it. So I guess it's not going to be that good tonight.
No,
except in Battersea.
Okay, thank you. Leslie?
No, I don't have anything to show, but I do have a question.
Sure.
That I got behind downloading Regulus. And when I was trying to do it yesterday, I got something that was not a proper PDF file. and was much too small and wouldn't open. And I kept getting this for January and February, and I tried to reproduce it tonight, and then I could have something to show, and it didn't work. It was all fine. So does anybody know what's going on with this?
We will check into that. We did a recent update of the Drupal core of the website yesterday or the day before, and ran into dependency version errors up the wazoo, and we're thinking about having to replace the entire website again because things are just getting incompatible with each other. But if you've got the issues now, that's great. We can always email them to people if the website's not working.
Yeah, well, it was working tonight. Otherwise, I'd have something to show. But it was some strange. I've had this happen before, actually. That it was, instead of calling itself a portable document format or something, it was calling it Microsoft format, but it had a PDF extension.
Very strange. Well, if it happens again, send us an email with the date and time and the web link that it happened to, and we'll follow it up.
Yeah. Okay.
Thanks, Leslie. Okay, anybody else on? Peggy?
I did see the planets briefly, and I have been out a couple of times. That's about it.
Okay. We'll carry on from the room here. Let's see, Donna. No, nothing for Donna. Okay, Steve. We're getting you a microphone.
Okay, that's
Okay, it's been a dismal month for me, but I've had 3 fairly good nights, and I got caught up on my galaxies in Leo and Virgo.
And
And that's it.
And that's it.
okay.
An upgrade, you're off it.
Yes.
Yeah.
All of a sudden, he's going to be telling us that his galaxies are much, much better.
That's right.
Any observing reports?
Haven't been out there, unfortunately.
That counts.
Maybe
That's
next
okay,
month.
Peter. That's okay. We all are in that boat. Roger.
I've just been dealing with equipment issues. Last time I was out, it was so cold that the focus just
cold
froze up.
was it?
It was so cold the autofocuser froze up.
Oh.
So I'm also in the middle of changing the optical configurations around. So waiting for a couple of clear nights so I can put it all back together.
Kim, can you re-am the webcam to follow us, sir?
Is that also involving your mount?
Nothing for me. Too cold and too windy, too cloudy.
There we go.
Mark?
No, well, I had been hoping to get another crack at the Jupiter-Venus conjunction, but I think the weather gods wanted me to stay inside.
Did you get any at all?
I did get one which I showed last meeting, but
That's more than the rest of us.
yeah, nothing new.
Nothing to report.
Nothing to report,
Nothing
Brian?
to report, no.
Rick?
I have been observing, I've had 14 sessions so far this year.
Two. I've had 2.
Yeah, but you spend all your time working or sleeping to be able to go to work or something. The Boltwood scope has been working fine. The Hank scope has been just hell on earth. Its controller, the Gemini controller would not start. So it took me a week of messing around, drying it out and doing, I don't know what all. And finally it worked. And I got about 2 hours of data, and then the software on the computer crapped out, drove the focuser 12,000 steps out of focus, at which point, of course, it couldn't see anything. So the whole script just collapsed, and I have not yet resolved that issue. So it's been 5 weeks, I think now, since I've taken hardly any data with the Hank scope. But anyway, Jeanette will talk about the other thing we observed.
Jeanette.
Yeah, my optics were working fine, so I stepped out onto the deck and with Rick, and we observed the rendezvous of Jupiter and Venus on March 2nd.
I'm so envious. I missed them.
I don't look up in the wintertime.
Okay, let's leave it at that.
No, the other night, John and I did actually look up. Remember, we looked at Jupiter and Venus up in
Yeah,
the west?
yeah.
And we also checked out Orion. And we talked about a few stars and that was about it.
2 minutes.
And you weren't paying attention.
Okay, Kevin.
Well, I am really enamored by the British Astronomical Association thing that we saw that we presented to them about an astronomer who sketches the sky every day. And the first 20 days of January were all gray. I don't know if you remember that painting. He painted a little sketch. And so what we tend to do, we've been watching a lot of online video conferences. And one of the advantages of being a radio astronomer is that we don't give a rat's patooey about clouds. We can look at radio stuff. And this past weekend, we took our sudden ionospheric disturbance radio telescope system and we wiped it. Well, we actually saved the old chip and put it in a little plastic baggie, but we rebuilt the system from scratch. Brand new operating system, same old Raspberry Pi, brand new software to do data logging. And Kim, what else did we do?
You fixed the code.
We got it working. We programmed in Python. We unscrambled, we troubleshooted log file not found, stupid errors, and to the point where we are now running new software and we are getting 2 station data again, NA Cutler, Maine, and also NML North Dakota. So these are just flipping around UT time. There we go. Sometimes you have to refresh the web page to get the cache to clear. So we are getting a signal out of Maine. We're not really sure if we're getting a signal out of North Dakota or not, because this has only been functional for about 2 days now. But hey guys, it's radio telescopes. It's cloudy skies. It's awesome.
The data is also being uploaded to Stanford University.
Yeah, so we're getting it
now. So that's like 2 years, 2 years,
2 years of data.
2 years of not being able to upload it.
We have the data, Stanford does not.
Yeah.
The Radio Jove telescope system continues to work fine. We're about to spend more time with it to learn more about it, to try to get it data archiving with, what's the place where we data archive Radio Jove data? I don't know because it hasn't been working either.
Florida.
But we're about to lose Jupiter, as was mentioned. It's heading towards the sun. So any fun Jupiter radio stuff, we're not going to be doing anymore for a while until it comes around the other side. Noise. So you know what light pollution is to visual observing. This is radio pollution. Some of it's scientific instrumentation, probing the ionosphere to listen, transmit, listen to see what its status is. Others are lightning. Oh, we've got some great lightning data in the summer. If you've ever seen some of these, it's wall-to-wall spike.
So did you pick up the thunder snow the other?
I do not believe we did pick up the thunder snow, but then we haven't been looking for it because by the time we heard about it, it was gone and nobody said there was some thunder snow at 1400 Eastern Standard, so we can go and check, right? Anything that gets above a certain threshold, we have an audio recording of, and that's kind of cool too, to listen into what it is. We seem to be in a radio dark zone here for WWV. A lot of you live farther away from us, so you may actually be able to pick up the time signal from Colorado. We cannot where we live. But what happens?
CHU either.
We can't get CHU either. But what happens occasionally when there's solar storms and ionospheric disturbances is that the ionosphere changes, the bounce zone changes, and we do start picking up on our data, beep, 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 and the radio time signal and the human voices. And it's really irritating because it can it just overwrites the data of what you're listening to otherwise because it's so much stronger. So that's about all Kevin's got to say because he hasn't even snow plowed out to the observatory.
So what is it you are picking up? Like, what is the force?
Most of it's going to be solar data. So let's go back to yesterday if we can. So you tend to get the galactic core, sorry, as it goes by at a sidereal rate, so it moves around. you tend to get X-class flares and other large events that happen. And we've actually got some of those tagged and pulled out of the data so you can actually see them better. Like an X1 solar flare in 2021, you know, it basically goes off the scale. This mouse doesn't seem to want to work too well on this surface. And another X-class flare in 2022, and an X1 non-event. And that's one of the weird things about X-class flares in the ionosphere. The Super SID program radio telescope will detect them and show a big spike. This particular X1 flare on May 3rd, 2022 caused a radio blackout. It affected the ionosphere such that we picked up nothing. And you'll see these big black radio blackouts. What's the term? Radio blackouts. And this can affect other things like GPS. So if you are driving along, following your GPS flawlessly in a solar storm, you may not end up where you think you are. Something like that. I was going to ask Steve, how far away is your observatory from your house? And how do you get there in snow this deep? Does Donna go out and shovel? So we shoveled out to the observatory Cayman's Bay Stat, and it was quite a feat. The next day we took the snowblower around the backyard and did that. I have yet to get out to my observatory, which is a little bit farther out through the gates, which you can't open because they're snowed in and iced down. And so I'm kind of waiting for everything to thaw before I can get back to the observatory again. And I know Malcolm Park's observatory is quite a distance away from his house. Roger, how far away is yours?
100 meters. I only have a few centimeters of snow.
A few centimeters. We got 35 centimeters. Wow. I think we'll have to move there. And so Brian's in his backyard, no observatory yet, no observatory yet. How far away are you and what do you do?
Probably 25 meters or
Yeah.
something, but it's on the other side of our parking area, so I have to shovel the whole thing.
You have to shovel it anyway.
Our total driveway is about the same area as a single car driveway.
Yeah.
225 meters long.
And ours is about 50 meters long in the driveway, but that's not anywhere near the observatories. Okay, that's all I've got. Thank you very much.
You bring up my picture?
Was I sharing that? I probably wasn't. Oh, well, I got to talking and that's what happened. Sorry, guys. You should have said something, Susan. Okay, so we're looking for Kim's picture.
I heard you.
You know, but you didn't see me. That's the problem. Oh my goodness. Okay, this time we're going to share it. There you go.
This is this picture of the sun that I took today. This is hydrogen alpha. And I actually had the 2x Barlow on the Solar Max 60. And I was just floored by this. I did not want to come in here to Kingston because I was getting this as we had to get ready to leave. So I was actually able to catch, there's spicules that are, if you can see the edge, and there's actually prominence, there's little filaments that are coming off of the sun. This is the only one I could process quickly before I had to leave. So I took a lot more, and I actually took some just without the Barlow just because I wanted full disc. But this is with the Barlow, and it's amazing. I'm pretty happy with this because I can actually see a lot of filaments that are on there. And this is actually a sunspot group that's in the south, 3245, that actually gave off a couple of flares. And the one that's in the north, this one here, 3242 is the one that's been giving off the X-class flares over the last few days. So as you can see right here, this little white spot, that's an active region that's starting up. Anyway, that's the only one I got processed.
Nice, Kim.
Thank you. And that is it. Does anybody have any questions or anything they want to bring up in Zoom land?
Those are pretty good pictures of the sun there, Kim.
Thank you. Anybody have anything from the floor? If not, then I guess we shall wrap up our meeting. And we'll see you again next month. Again, we are going to have Chris Larson give us a talk on April 12th. And for those members that want to do the social, we'll see you again on Wednesday night. So thank you all for coming and have a great evening.
And
Take
I'm
care,
just gonna
everybody.
throw in that if you're looking for any and all of Rick's What's Up in the Sky, it should be in Regulus or
Yep.
will be in Regulus or
It should be online.
be on the webpage or somewhere.
Rick's What's Up in the Sky will be on the website
Yeah.
and
And on the All Things Astro Google Calendar.
on the Google Calendar, and then we'll have the meeting will be up on the YouTube channel in a few days.
Okay, great.
Thank you, everybody, for coming. Take care. We'll see you later.
Okay, so John, you can stop recording. And I think